Consider the common kitchen foil. If you hold a sheet of it between your thumb and forefinger, it measures roughly 0.016 millimeters thick. It tears under the weight of a stray breeze. It is a disposable afterthought of a modern grocery aisle. In the humid twilight of August 1977, a small team of engineers at the Jet Propulsion Laboratory in Pasadena, California, stood around a clean room table. With gloved hands, they wrapped sheets of this exact consumer-grade material around the exposed wiring harness of a 3-axis stabilized space probe. They were not insulating it from the cold. They were terrified. They knew that if they did not shield the machine's internal veins, the ambient invisible electrical storms of a world they had never seen would fry the craft's primitive 8 kilobyte brain before it could ever look back at the Earth. To understand Voyager, you must understand the sheer fragile audacity of its era. It was a machine built before the advent of the microchip. Its primitive data storage was not a solid-state drive, but a mechanical digital tape recorder. A system of spinning wheels and magnetic ribbon that clanged in the absolute vacuum of space. Its onboard computers possessed less computing power than the key fob you use to unlock your car today. The entire apparatus ran on less electricity than it takes to power a single light bulb. And yet its itinerary was nothing short of madness. Jupiter, Saturn, Uranus, Neptune, and then the endless, uncharted void. But as the launch window drew near, a mathematical shadow hung over Cape Canaveral. It was the tyranny of the Tsiolkovsky rocket equation. This is the unyielding law of spatial physics that dictates a brutal loop. To push a payload out of Earth's heavy gravitational grip, you need fuel. But fuel has weight. So to lift that fuel, you need more fuel. To lift that fuel, the rocket must grow exponentially larger until you are building a skyscraper of explosives just to launch a suitcase of instruments. By every metric of conventional chemical propulsion, Voyager was an impossibility. To send a craft to the edge of a solar system under its own power would have required a rocket fuel tank the size of a small mountain. We did not have the mountain. We had a 600-pound box of aluminum foil and analog tape bolted to a tiny column of fire sitting on a launch pad in Florida. Yet today, as you listen to this, that fragile box is over 14 billion miles away. It is moving through the absolute zero of interstellar space at 38,000 miles per hour. It has left the sun's protective bubble entirely behind. We did not give it the fuel to get there. We couldn't. Instead, we forced a giant to give up its momentum. Let's step away for a bit. Let's come back to Earth. Go to an isolated railway crossing in the dead of winter. Stand safely by the steel tracks. Imagine a massive locomotive weighing 200 tons screaming towards you through the fog at 60 miles per hour. It represents an immense, terrifying concentration of kinetic energy. Now imagine you are holding a regulation tennis ball. You step forward and you toss the tennis ball down the tracks directly onto the face of the upcoming train at a gentle 30 miles per hour. What happens at the point of impact? Your instincts tell you that the ball simply bounces back. But the physics of an elastic collision inside a moving frame of reference reveal a deeper secret. The ball does not just return to you at the 30 mile per hour you gave it. Because it struck an oncoming wall of overwhelming mass, it absorbs the momentum of that wall. The ball reverses direction and flies away from the locomotive at 90 miles per hour, 30 miles of its own initial speed plus twice the speed of the train. The ball has been violently, miraculously accelerated without any internal engine. And the train has slowed down. Because of the microscopic impact of the tennis ball, the 200-ton locomotive has lost an infinitely small, unmeasurable fraction of its speed. The energy was transferred. A theft has occurred in plain sight. In 1965, long before Voyager was even a blueprint, a graduate student at the Jet Propulsion Laboratory named Gary was sitting at the desk covered in handwritten orbital logbook. He was charting the long-term movements of the outer planet. As his pen traced the curves, he noticed a geometric alignment that has not occurred since the presidency of Thomas Jefferson, an alignment that happens only once every 176 years. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would swing into a perfect cascading celestial arc. Gary realized that if humanity could launch a probe at precisely the right microsecond, we wouldn't need a mountain of rocket fuel. We could use the gravity wells of the giant gas as an interlocking sequence of cosmic trains. In the July of 1979, Voyager approached Jupiter. To the tracking stations on Earth, it was a terrifying spectacle. The probe was falling down the throat of the giant, pulled in by the gravitational mass 300 times greater than our own planet. It accelerated to breakneck speeds, flying into the low plasma torch, an invisible donut of intense radiation that screamed against the kitchen foil shielding. Inside the control room, engineers held their breath as telemetry dropped. But Voyager did not crash. It did not aim for the center of the planet. It intentionally crept up from behind, stealing into the planet's shadow along its path of travel around the sun. As Voyager fell through the gravity well, it hooked onto Jupiter's immense orbital momentum. The planet pulled the probe along with it, whipping it around its backside like a stone flung from a leather sling. When Voyager finally broke free of Jupiter's gravitational grip and shot back out into the dark, its internal engines had not fried a single drop of fuel. Yet it had gained 16,000 miles per hour of velocity. It had been flung towards Saturn with enough speed to escape the Sun's family forever. And just like the tennis ball on the frozen tracks, the cosmic ledger had to be balanced. When Voyager sped up, Jupiter slowed down. Because a 600-pound metal box interacted with a planet weighing over 2 million trillion tons, Jupiter lost its footing. The equations show that because of that brief July encounter, Jupiter's orbital journey around the Sun slowed down by roughly 1 foot every trillion years. We altered the giant clockwork of the solar system to throw our voice into the interstellar night. There is an inherent arrogance to how we document the history of human progress. We tell ourselves stories of conquest, of breaking things to bend them to our will. We build larger engines, excavate deeper mines, ignite more violent explosions. We operate under the delusion that to master the universe, we must dominate it through sheer brute force. But Voyager tells a quieter, more elegant story. On board that craft is a golden phonograph record. On it, we etch the sounds of rain, the laughter of children, a mother's first word to her newborn child, and the music of Bach and Blind Willie Johnson. It is a message in a bottle, wrapped in kitchen foil, drifting through a desert of stars. Voyager reminds us that we are small, fragile things living on an island of dust. We cannot outmuscle the physics of the cosmos. We cannot outburn the gravity of the stars that birthed us. The true genius of a species is not our strength, it is our capacity for leverage. It is the quiet mathematical humility that allows us to look at a giant, roaring planet and see not an obstacle but a partner. It is the realization that if we sit long enough with the geometry, we will observe the turning of the great wheels around us. We can find a way to slip through the gears of eternity. Tonight, step outside. Look up past the city lights. Find the faint, steady, amber gleam of Jupiter hanging in the velvet black. It is still there, turning its massive bulk in its lonely orbit. But it is moving just a fraction slower than it did last century. Because 49 years ago, a collection of fragile creatures on a blue world reached out into the dark, asked a giant for a push, and stole a second of its time to buy their immortality.